So again, here are the sinusoidal functions that we're familiar with. When we say y is equal to a times the sine of b times x minus c, make sure that you're actually writing those brackets down. Or of course, y is equal to a times the cosine of b times x minus c. B is important, it's the frequency, and we use the frequency to calculate the period. We need to be certain that we know not only what the value of b is, but that we're clear on the value for c. C is, of course, the horizontal shift. So there are some instances where the phase shift, c, can be hidden if we haven't yet factored out b. If you look at the equation on the left-hand side, it doesn't quite fit the format. We still have 3x, so we can identify the value for b. So here we have b is equal to 3, but we're not certain about the value for c. In this case, c does not equal negative pi over 6. And that's because the left-hand side and the right-hand side here are not equivalent. So while the right-hand side does match the general formula of our sinusoidal, it's not equivalent to the original function given on the left-hand side. Here's our original function again, with its factored form on the right. So when we have 3x plus pi over 6, in order to clearly indicate the value for b and to reveal the value of c, we need to factor out a 3 from both terms. So that means we're dividing both sides, both terms rather, by 3. That leaves us 3x divided by 3 with an x, and the second term will be pi over 6 divided by 3. So pi over 6 divided by 3, which we should write as pi over 6 times 1/3 to show that this gives us pi over 18. So pi over 6 divided by 3 leaves us with pi over 18. So as a result, the value for c, the horizontal shift, is negative pi over 18. Sometimes this is easier to see if you start with the factored form and using distributive property, convert it. 3 times x gives us 3x, and 3 times pi over 18, 3 times pi over 18 does in fact give us pi over 6, or pi over 6. So just be sure before you write down the values for b and c that your equation is in the correct form. Let's look at 2 more. Here we have y is equal to negative 2/3 sine 4x plus pi. Right away, we've hit one of those issues where we have not yet factored out b from both terms. So we'll write this as y is equal to negative 2/3 sine, and then factor out the coefficient for x, the 4, from both the 4x and the pi. 4x divided by 4 leaves us with x, pi divided by 4 leaves us with pi over 4. If you're not convinced, use distributive property. 4 times x is 4x. 4 times pi over 4 is just pi. Yes, we factored that correctly. And one more time, I'll write out the general function. So we can see from our modified equation here that a has a value of negative 2/3, b has a value of 4, and c has a value of negative pi over 4. All right, so our amplitude, therefore, given that it's the absolute value of a, will be the absolute value of negative 2/3, which is positive 2/3. The period of the function, as always, is 2 pi divided by the frequency, or 2 pi divided by b. In our case, that will be 2 pi divided by 4, which simplifies to pi over 2. So we'll take a distance of pi over 2 to go through one cycle of our function. The horizontal shift that we uncovered, our value for c, is negative pi over 4. I like to indicate the tick marks as well. So since it will take us from 0 to pi over 2 to get through the function, the important things will happen here. They'll happen at the quarters, 1/4 of the way through from 0 to pi over 2, halfway through, 3/4 of the way through, and all the way through. So we'll take the value for the period, pi over 2, and multiply it by 1 over 4. That gives us 1 over 8. Again, the tick marks here don't match well, so I'm not going to use the values that are given, and we'll indicate our own. So we know it will take from 0 to pi over 2 to get through one cycle of our function. Even if it's shifted, this is still true. So I'll label the fourth tick mark as pi over 2, and then we'll move in steps of pi over 8 to get there. 4 times pi over 8 should get us to the end of our period, pi over 2. So we have 1 times pi over 8. 2 times pi over 8, which simplifies to pi over 4. 3 times pi over 8, so 3 pi over 8. And then finally, 4 pi over 8. Does that simplify to pi over 2? Absolutely. So we've done this correctly. We'll be shifting to the left, so I'm going to add a couple more tick marks to the right. Negative pi over 8, negative pi over 4, and negative 3 pi over 8. Now the vertical axis. Our amplitude is 2/3, so maybe I'll just write one tick mark and label it as positive 2/3, and 3 squares down as negative 2/3. Now that our axes are set, let's start by graphing the unshifted function. Here we're graphing sine. So once again, in general, sine will start at 0, hit its maximum in the first quarter, return to 0 halfway through, 3/4 of the way through, will hit the minimum value, and all of the way through will hit 0. That's true for values where a is positive. Since our value for a is negative, this gives us the reflection of sine. So we, instead of starting at 0 and going up, we'll start at 0 and go down to the minimum. 0 is still 0, regardless of what we multiply it by. And then in the third quarter, we hit our maximum until we end where we started. So we'll start at 0. 1/4 of the way through the function, we'll hit our minimum. So that's negative 2 over 3. Halfway through, we hit 0 again. We cross the x-axis. 3/4 of the way through, we're at the maximum of our function, and all of the way through, we're at the end of our period of pi over 2. I'll just connect these with rounded dotted lines, because this is our unshifted function. Our horizontal shift is negative pi over 4. How many tick marks is negative pi over 4? Again, we're fairly lucky because it's an actual number of tick marks. It's not half a tick mark or 2.5 tick marks. To move a distance of pi over 4, I move 2 tick marks. So I'm going to pick up every single point that's currently on our graph and move it to the left by pi over 4, by 2 tick marks. So this one ends up here, this one ends up here, and so on. Start by drawing in our graph, just to draw in what we've got so far before it gets away from us. And there is one period of our function. If you wish, you can draw more by continuing the same pattern to the left and to the right. Let's do one more to make sure we've got this. This is a graph of cosine. I like to highlight that to myself first. The general form of the sinusoidal function is y is equal to a, here times the cosine of b times x minus c. And I notice that unfortunately, the brackets here have not yet been factored. So I can see that the value for a is 5 and the value for b is 1/2, but the phase shift here, the value for c, is hidden. So I'll have to factor out 1/2 from both terms inside the brackets. That gives us y is equal to 5 times the cosine of 1/2 times x plus, well, x plus pi over 4 divided by 1/2, which is equivalent to pi over 4 times 2 over 1, and therefore equivalent to pi over 2. So we have 1/2 times x plus pi over 2. So we find that our value for c, our horizontal shift, is negative pi over 2. And with that, we're ready to find the amplitude, the period, and the shift. The amplitude, as always, is the absolute value of A. So in our case, given that it's the absolute value of 5, we just get 5. The period is equal to 2 pi over b, 2 pi over the frequency. For us, that will be 2 pi divided by 1/2, or 2 pi divided by 1/2 is the same as times 2, or 4 pi. So it'll take us from 0 to 4 pi, a distance of 4 pi, to get through a whole cycle. The horizontal shift has a value of c, and we revealed that this was negative pi over 2. Finally, to give us a hand graphing, let's have a look at what the tick marks will look like. It'll be the value of the period, 4 pi, divided into quarters, because the interesting things in a cosine or a sine function happen at the quarters. 4 pi divided by 4 is just pi. Again, these aren't going to serve me all that well, so I'm going to rewrite the values along the x-axis. Let's use the ones that are already given, so the same location for the tick marks, but I'm not going to label them the same way. So the distance between any two tick marks is pi. So from 0 to the first tick mark, we've traveled a distance of pi. From 0 to the second tick mark, a distance of 2 pi, 3 pi, and 4 pi brings us to the final tick mark. And that brings us through one cycle, one period of the function. Let's add some more in the negative direction. So we have negative pi, negative 2 pi, and we could keep going if we like. I'll arbitrarily label this as positive 5 and this point as negative 5. Again, with our axes set up, we're now ready to graph this function. This is cosine, and cosine normally starts at its maximum. Does this one start at its maximum? Yes, because the value for a was positive. So it starts at its maximum, 1/4 of the way through the function, it crosses over the x-axis. Halfway through the function, it's at its minimum. 3/4 of the way through the function, we cross the x-axis again, and we end where we started. And that brings us to 4 pi. So I'll use a dotted line to indicate that this is not our final answer since we haven't shifted it yet. What is our shift? The horizontal shift is negative pi over 2, so we're going to be moving to the left. How far is a distance of pi over 2? Well, if one tick mark is the distance of pi, halfway between tick marks, we've traveled a distance of pi over 2. So I'll indicate positive pi over 2 on the right-hand side of the y-axis and negative pi over 2 on the left-hand side. In other words, every single point is going to move to the left by 1/2 of a tick mark. So I'm going to move each point to the left by the distance of 1/2 of a tick mark. I'll connect those dots. It's harder with this pen to connect using solid lines. I'll connect those dots smoothly as I can to draw our cosine function. And there we go. Given a function, we can now sketch a graph of that function.